We can hit the recording. It's recording. Okay, good. Good morning, everyone, for this distinguished webinar series in AI and cybersecurity. With us today, we have Dr. Massimiliano Albanese, Associate Professor, Department of Information Science and Technology, Associate Director, Center for Secure Information System at George Mason University. Dr. Max is also an Associate Chair for Research of the Department of Information Science and Technology. He received his PhD in Computer Science and Engineering in 2005 from University of Naples, Federico II, and joined George Mason University in 2011 after serving as a postdoctoral researcher at the University of Maryland, College Park. His research interests are in the area of information and network security, with particular emphasis on modeling and detection of cyber attacks, cyber situational awareness, network hardening, moving target defense, configuration security, and vulnerability metrics. Dr. Albanese has participated in the sponsored projects totaling $13 million, with a personal share of $3.5 million. He holds 2 US patents and has co-authored a book and over 70 publications in peer-reviewed journals and conference proceedings. Dr. Albanese is one of the 3 recipients of the 2014 Mason Emerging Researcher Scholar Creator Award, one of the most prestigious honors at Mason. He has served on the technical program committee of numerous conferences, and he is a member of editorial board of IEEE Internet of Things Journal, Springer International Journal of Information Security, and Elsevier Computer and Security. Dr. Max, it's a great honor to have you part of UND's distinguished webinar series. Thank you so much for agreeing to do this webinar series. We are so grateful for your time and effort for making this presentation happen. The floor is yours, and
thank you. Thank you so much for thank you so much for the invitation, and thank you so much for the nice introduction. Okay, so let me go ahead and see if you are able to see my full screen again.
Yeah, we can. I think great.
Okay.
So you have about 45 to 50 minutes, and then we can have 10 minutes for Q&A at the end.
Okay, perfect. So the title of my talk is From Cyber Situational Awareness to Adaptive Cyber Defense, and the role of vulnerability analysis in leveling the cyber playing field. I'll skip the introduction since you did a very comprehensive introduction. Just a quick disclaimer, if you go to our website and see something different, it's because as of today, George Mason University has a new logo, and I didn't have the time to update my materials to reflect the new branding, but the one on the right is the new logo as of today. This is the outline of my talk. I'll start with giving some motivation about this work. And I'll then explain the 2 main areas of research, the cyber situational awareness and adaptive cyber defense, and explain how these 2 converge to help leveling the cyber playing field. And then specifically, we'll dive into vulnerability analysis, which represents the bulk of my recent work. So to start, the idea behind this work is that in the cyber world, there is an intrinsic asymmetry between attackers and defenders, and that asymmetry tends to favor the attacker, because the defenders have to protect from any possible way the system could be attacked, while on the other side, attackers only have to find one single vulnerable entry point or entry path in order to succeed. So the goal is to reduce this gap and possibly invert the rules. And I apologize, my voice is a little bit rough. I had lost my voice in the last couple of days, so I just recovered. Now, to give you a visual of this, this chart tries to conceptualize the notion of the effort that the attacker has to put to attack and the defender has to put to defend from the attacks. And as you can see, of course, the defender has to put more significantly more effort in order to defend. The goal of cyber situational awareness is to push this boundary down, but by improving the defender's knowledge of the cyber landscape. On the other side, we can push the attacker's effort up by using adaptive cyber defense, which includes things like moving target defense, deception, and so on. So ideally, we would like to reduce this gap as much as possible, and even better, we would like to revert the game in favor of the defender. So that's the ultimate goal of these two areas of research that are converging to achieve this goal. Now, let me speak a little bit about cyber situational awareness. Cyber situational awareness is a process that enables defenders to acquire, understand, and leverage information about the environment. And it can be broken down into 3 steps: perception, comprehension, and projection. In the perception stage, you essentially are gathering information from the environment. And environment can include both, the attackers and their motivation, behaviors, and your own systems. In the second stage, which is comprehension, you try to make sense of all of this information, try to interpret that information and extract actionable intelligence. And then in the third stage, which is projection, you try to use all of this information that you have acquired and learned and process it to try and predict what can happen next in order to be able to proactively defend from future attacks. And this part of the work was a result of a multi-year MURI project with other 3 universities. And at the end of this project, we came up with the key questions of cyber situational awareness. So given a system and given a situation under which the system could be under attack, defenders have to ask this 7 questions. What is the current situation? What is the potential impact of what's going on my system? How can the attack evolve in the future? What is the behavior of the attacker? How can I understand how the attack was possible in the first place? So this is the forensics part. Can I rely on the information that I've gathered from the environment? So there is a quality assessment aspect to it. Can I predict what's going to happen next? And can I make this whole process scalable so that I can deal with larger networks, larger volumes of attacks, and so on? So at the end of this project, we came out with an overall framework for cyber situational awareness. This, of course, was the contribution of 4 different groups across 4 universities. And the part that I've highlighted in green is the one that GMU mostly contributed to. I'm not going to go into details of this because, of course, this is like 5 years worth of work. But just to tell you that out of this, we had some interesting contribution. And without going into details of those, one contribution that I want to highlight is this notion of attack scenario graphs. Probably most of you are familiar with the notion of attack graphs, are graphs that represent vulnerabilities in a system and the relationships between vulnerabilities, which enable analysts to analyze how multi-step attacks can occur. What we did here, we connected the notion of attack graph with the notion of dependency graph that identifies functional dependencies within the system and between system components. Some of those dependencies may be documented, some of those dependencies may not be documented, and we have come up with solutions to infer those dependencies from network traffic and other observations of the system. But ideally, what this allows to do, it allows to understand how every single step of an attack can propagate damage across the system. So to give an example, if an attacker compromises a vulnerability VC, that vulnerability will affect one component on in the dependency graph, and the number on those edges connecting vulnerabilities to the nodes in the dependency graph give you the exposure factor, which is the relative damage that is inflicted to the asset if that vulnerability is exploited. In this particular example, you can see that this is labeled as 1, which means that 100% of these resources will be compromised if this vulnerability is exploited. Now, in a typical attack graph, once a vulnerability is being exploited, the attacker can move to the next vulnerability, which in this case could be either VF or VD. So again, the attacker now has a choice, and what we need to understand is which option that the attacker can take could have the most damage, because that will help us prioritize where to defend our system. Now, you can see that if the attacker exploits VD, 70% of this additional asset is compromised. Now, from this graph, you can also see that the other components that depend on this compromised asset were already compromised during the previous attack step. So there is no additional damage that propagates to those components. But if the attacker decides to exploit VF, then the component that will be directly affected is this, I think, HF. And because of the nature of the dependency, you will see that the damage this time will propagate and compromise, affect other components, which are HA and HS. So essentially resulting in a much larger damage. So again, this tells you that if we have to prioritize what to do next, if we know that the attacker has just exploited VC, we know that we need to take care of VF rather than VD, because that could lead to potentially more damage. So this piece is important because, as you will see through my presentation, there are several pieces of work that we did after this that build upon this, this model. Now, the other major side of this research is, as I mentioned, the adaptive cyber defense portion. And this, again, was the result of another MURI project, again, with 3-4 universities. And the idea behind it, the basic principle is that if you look at traditional defenses, they are static. And once defenses are static, it's just a matter of time for the attacker to figure out the configuration of your system, to learn enough information to be able to plan a successful attack. So this line of research led to a number of different principles and techniques called adaptation techniques that essentially consist in making the system dynamic so that increases the complexity for the attacker. And one prime example of techniques that came out of this line of research are those commonly referred as moving target defense. Essentially, you make the attacker's target constantly moving, so the attacker is to constantly learn in order to be able to craft a successful attack plan. And this again led to a very complex framework involving a lot of different components. I'm not going to focus on this one because there will be another talk per se. I just want to highlight some important principles that inspired this work or were the result of this work. One is this notion of adaptation in depth, which is an extension of the traditional notion of defense in depth. Now, if you have this network, there are multiple things that you can do at the same time in order to increase the complexity for the attacker. You could add diversity. So in this particular cluster here, you have a bunch of servers. If they all have the same configuration, once the attacker is able to exploit one of them, and he can exploit all of them. Making them diverse increases the complexity for the attacker. The other thing you can do is you can add honeypots, honey-nets, or what we called as an extension of honeypots and honey-nets, distraction cluster, which was a paper that we wrote a few years ago, which is just a slightly more advanced concept than the honeypots. You can add deception so that a server from the eyes of an attacker looks like something else, like a printer, for example, reducing the chances it will be attacked. You can add proxies between your DMZ and internal servers in order to try and prevent denial of service attacks. And the other piece of work that we did was about a dynamic detector placement. So sophisticated attackers may also have mechanisms to identify the presence of intrusion detection systems and similar sensors that you can use to monitor the traffic. So by making the deployment of sensors dynamic, it can also increase complexity for the attacker because the attacker will have to try and adapt to your dynamic deployment. So the example here is that this intrusion detection system represented by this human figure moves around the network. It doesn't stay on the same system all the time. The related notion that enables this is the notion of external attack surface. And what it means essentially is that the way the system looks from the point of view of an attacker is different from what the system really is. And the end goal of this is for the attacker to make attack plans based on an incorrect view of the system. An analogy that I like to use to explain this concept is suppose that this is the object that you want to hide from the attacker. In order to deceive the attacker, you may make this object look different in shape, in color, in texture, so that the attacker plans based on this incorrect view of that object. Now, translate that into the cyber world. If you have this network and you want to hide it from the attacker, you make it look like this. And different colors means that the configuration that the attacker sees is different. In this case, for example, I just want to point out this example of the public server on top of here. You can see that the attacker sees two servers instead of one. And the way this can be done is using a moving target defense that switches or rotates IP addresses. So when the attacker pings that system, one time gets a response from an IP address, one time gets a response from a different IP address, he may think that there are two servers in a, let's say, load balancing configuration, which makes potentially the attacker more complex, because for the attacker to take down the service, he knows that he has to take down two machines instead of one. And he may simply give up attacking that particular machine. From a conceptual point of view, essentially what we're trying to do here is, in the ideal situation for us, the attacker should just use a random guesses to figure out the configuration of the system. What we can do is we can do better by skewing the attacker's probability distribution toward the incorrect configuration. So in this case, for example, the green dot represent the correct value of a system parameter that the attacker is trying to guess. And we want to present information to the attacker so that he believes that the most likely value for that particular parameter corresponds to the red dot, which would be an incorrect conclusion from the side of the attacker. And to bring this to fruition, we came up with a model that essentially tries to formalize this notion of attack surface and how we can manipulate a system real attack surface to present the attacker with a deceptive attack surface. And this graph represents exactly that concept. Each node in this graph represents a variant of the attack surface that we present to the attacker, and the age represents one atomic manipulation of the attack surface that we do to transform one attack surface into the other. And we can measure the distance between two attack surfaces as the distance between two nodes in this graph. So in other words, we were able to formalize in a mathematical framework this notion of attack surface and distance between attack surfaces. So let's say that covers the the overview, the general framework in which most of my research can be framed. In the last, I would say, 3 or 4 years, I've been mostly focusing on vulnerability analysis and vulnerability metrics. Now, the problem statement behind this line of research is, as you know, every system may present a very large number of exposed and patched vulnerabilities. And system administrators have to take actions to mitigate or remediate those vulnerabilities. But given the large numbers of vulnerabilities that exist, methods needs to be developed to be able to quantify the effect of those vulnerabilities and try to prioritize based on some notion of severity. So there are several organizations like NIST and MITRE that come out with solutions to assign numerical values to different vulnerabilities and weaknesses. And that has resulted, for example, in the CVSS, Common Vulnerability Scoring System, in the MITRE's top 25 CWE ranking, which is illustrated in this slide. This is what MITRE publishes on a yearly basis. This is the most recent versions, the 2023 CWE top 25 most dangerous software weaknesses. A CWE, or software weakness, it's a more abstract concept with respect to vulnerability. Each CWE essentially represents a class of vulnerabilities with similar features. So, for example, if you pick the top CWE is out of bound write. So these are all those vulnerabilities that result in an attacker being able to write outside of certain memory range. So what MITRE does, publishes this yearly ranking of vulnerability of CWEs. Now, so what are some of the problems in the current state of the art? So one of the problems is that, yes, there has been a lot of work done in the space of vulnerability analysis, but the result is that there are a lot of different tools that are pretty much disconnected from one another. We have vulnerability scanning tools. We have vulnerability scoring frameworks like the ones that I've just mentioned. We have attack graphs like the whole literature of that graph that I also worked on. We have network hardening methods, but there is not yet a framework to bring all of these tools and those capabilities together. So, and this is what this part of my research tries to address. One other problem with one of the most commonly adopted vulnerability scoring system, that is CVSS, is the fact that this system is very coarse. If you analyze it carefully, you will realize that it only allows for 270 distinct values of the severity score. And the reason behind it is because the severity score is composed of two scores, the exploitability score and the impact score. And the exploitability score, in turn, is a function of three submetrics: the access complexity, authentication, and access vector. Each one of those can only assume one of three distinct numerical values. So that gives you 27 different possible combinations. And on the other side, the impact score, which is given by this formula, it's a function of these three subscores. Each one can assume one of three values, but in this case, the three values for each are the same. So you do the math, is only 10 possible different values of this product. So when you have thousands of vulnerabilities and you only have 270 numbers to assign to them, clearly your ability to rank them and to discriminate between every pair of vulnerabilities is reduced. The other problem that goes hand in hand to what I just mentioned is the fact that the number of vulnerabilities grows continually. This is just a snapshot from today of the NVD dashboard, and it just shows you the volume of vulnerabilities that are processed every week, every month, every year. It's just outstanding. So in order to try and contribute to improve this area, we have developed what we call the Mason Vulnerability Scoring Framework, which is a framework that essentially incorporates vulnerability level metrics that advance the state of the art with respect to vulnerability scoring, and then combine those metrics to compile a weakness score similar to what MITRE does, but with some benefits that I'm going to describe shortly. And then we've been working also on what I call the attack volume metric, which is a generalization of the traditional concept of attack surface metrics. And last but not least, CVE to CWE mapping, which I'm not going to discuss in details here because there is not enough time to do so. So I've mentioned the Mason Vulnerability Scoring Framework. This is a framework that we have made available to the public. It's available at the URL that you see over there. And I'll say something about this later in my presentation. The logic behind our system of metrics is that for each vulnerability, there is an intrinsic likelihood that an attacker may exploit that vulnerability. And once that vulnerability has been exploited, it results in exposure, which results in damage. Now, if you look at the likelihood, there are several variables that can affect the likelihood. There may be intrinsic features of the vulnerability, which is what MVD tries to capture with CVSS. So the exploitability score of CVSS tries to capture how exploitable a vulnerability is based on certain features. But there may be other variables in your particular environment, your specific environments, that may increase or decrease the likelihood of an attacker to exploit a vulnerability. Similarly, on the exposure side, the exposure factor is simply the relative damage that a successful exploitation will cause to the asset. And in CVSS, that is captured by the impact score, but we argued that there could be more variables, whether specific features of the vulnerabilities or environmental variables specific to the environment in which that vulnerability exists, that may affect the exposure factor. And so that resulted in this system of equations to capture the exploitability likelihood and the exposure factor. And I'm going to go into details of each one of this. So this is our equation for the exploitability score. It's essentially the product of these terms divided the product of another set of terms. And the way these terms are formulated, number one, to be all normalized between 0 and 1. Number two, the variables x that you see at the numerator are variables that increase the likelihood of an exploit. So for example, the exploitability score from CVS is one of those. The age of a vulnerability could be another factor. The longer a vulnerability has been around, the more likely it is to be exploited. And this exponential formulation allows also to account for diminishing returns, because this term will go asymptotically to 1 when the value of the variable grows. And we do similar thing for the exposure factor. Now, to give you an example, a non-conventional example of what some of those variables that contribute to the likelihood to the exposure factor may look like, one variable that we consider is the availability of intrusion detection rules. If an attacker knows that a specific vulnerability is highly detectable because there are several detection rules that are specifically crafted for that CVE, the attacker may opt to choose vulnerabilities that are less exploitable, okay, with less intrusion detection rules. So the number of IDS rules is a factor that decreases the likelihood. So it is one of those factors that goes at the denominator. And this chart just gives an example of what that contribution could be. So everything else being equal, when you increase the number of intrusion detection rules, the likelihood of an exploit drops. And this parameter gamma that is used to multiply the exponent, it's essentially used to control the slope of this asymptotic trend. Now, of course, you can imagine that once there are a few intrusion detection rules for a specific vulnerability, that's enough to discourage an attacker. And there is no significant additional benefit if you double the number of those rules. So again, these equations try to capture that notion of diminishing returns on the effects of the different variables. One other important thing that we did was to say, okay, how do quantify how good a ranking is? An ideal ranking is a ranking in which there is only one element for each value of the rank. So, I mean, imagine a podium where you have three spots on the podium and you have 20 winners. Of course, that is not a good way of assessing the outcome of a competition. So this ranking, this formula, which is given here, it's essentially trying to capture how close our ranking is to one in which every single vulnerability gets a distinct numeric value. And without going into the details of this, this simple example here shows that by adding more variables in the computation of those scores allows you to refine the ranking. This middle table here represents the case where you're using essentially the equivalent of CVSS, impact and exploitability scores, and it shows that rank number 1 with this particular numeric value of the score has 867 vulnerabilities with that exact same score. And same goes on for the second position and third position. But if we keep refining it, we keep adding more information about the vulnerabilities, we're able to better discriminate between vulnerabilities and give unique scores to each one of them. So in this case, you can see in the first position, there are only 8, in the second, only 15, and so on. And this table on the right shows the two extremes. Scenario 1 is the one where we use the fewest number of variables, and scenario 7 is the one where we use the largest number of variables in our experiments. And now you can see that the quality of the score here, it's almost virtually 0. And for the scenario 7, it's very close to 100% for all cases. Now, next is how can we use this vulnerability level scores to compute a weakness level score, where weakness, again, it's a more abstract concept with respect to vulnerability. So in order to have a system that reproduces in principle what MITRE does, we came up with this formula. So this formula multiplies the cardinality of a weakness, so the number of vulnerabilities in that weakness, which could be hundreds or even thousands, but by the average likelihood and average exposure factor of those vulnerabilities. Now, of course, this is a step forward from MITRE because it's based on more sophisticated vulnerability level metrics, and it allows us to compute those rankings more frequently, not just on a yearly basis. But there is an intrinsic problem, and the intrinsic problem is that these rankings are not system specific, meaning that the score of a CWE is based on all known CVEs that are described under that CWE category, is not based on what may exist in a specific system. So if you look at any specific system and you look at a given CWE, there may be thousands of, like for example, SQL injection. There may be thousands of different SQL injection vulnerabilities across all known DBMSs. But in your system, you may have only a tiny fraction of those. So you want to customize the rankings based on that particular instances of CVEs that you have in your system. So in order to do so, what we did is we changed this formula. And as you can see, you can probably notice, this formula is a particular instantiation of the general formula that I explained before. The one that I used before was the most general formulation. And here I instantiated this formula with some specific variables, which are exploitability, age of the vulnerability, and IDS rules. And then what we did here, instead of calculating this aggregated score across all the CVEs that exist in a given CW category WI, we calculated just across the vulnerabilities that exist in your system. So this CS of WI means the CVEs from that CW category that you found in your system using, for example, a vulnerability scanner. So essentially, the output of the vulnerability scanner that you run in your system would become an input to the scoring system. And then we did a second iteration of this, and we considered the following. In your system, it may also be the case that you have multiple instances of the same vulnerability. So you want to take that information into account, because it's one thing that you have one instance of a not so severe vulnerability. It's a different thing if you have 100 or 1,000 instances of the same medium severity vulnerability. So the aggregate of all those vulnerabilities, even though each one of them individually is not so severe, may represent a more significant risk that you want to factor into your scoring. And this second iteration of the CWE metric that we propose does exactly that. In fact, the average severity of CVEs in a given CW category is computed by weighting, by assigning a weight to each individual vulnerability, where that weight is the number of instances of that vulnerability within the system. So this gives you a much more accurate ranking of CWEs that is customized to your system and takes into account not only what vulnerabilities exist in the system, but how many instances of each of those vulnerabilities exist. And what is the end result of this? So the end result is, you can see here that when you start from the initial ranking, the one based on the generic score, the one that does not take into account system-specific information, and you apply these two generations of metrics, you will end up with slightly different rankings where things can move up and down. In this case, CWE 79, which is the most severe according to MITRE, drops down into 17th position. The reason being that in the specific system where we run our experiments, there were very few instances of vulnerability in that CWE category. Therefore, that CWE was not so important for this particular system. And that system is described in these two tables on the test bed is described in these two tables on the left. So it was a group of 7 virtual machines with each one deploying a different set of vulnerabilities. and the specific vulnerabilities of which we had instances in the test bed are listed here. And feel free to interrupt if you have any questions. The other thing that I mentioned is the Mason Vulnerability Scoring Framework, which is, again, an online system that is available. You can go and request an account if you have an EDU address or official company address. So this system is composed of different modules. There is a data ingestion module that pulls data from different data sources, including from MVD, from IDS rules repository, and so on. And then there is a metric computation module that essentially implements all the metrics that I've described so far. And there is a ranking module that can be invoked to essentially generate different versions of the rankings. And then there is a graphical user interface that allows you to interact with the system. Now, this is how the landing page of the system looks like. It will present you with the most recent monthly ranking. So if you go now, which is, we are in April, it will show you the ranking up to March of 2024. And instead of being limited to the top 25, it ranks up to 150 different CWEs. The other important feature of this, which is not available with the yearly rankings from MITRE, is that because we compute this scores every month, you can also see, by hovering over this table, you can see the trends in the evolution of CWE scores. So you can see which CWEs have grown in severity over time, which CWEs have become less severe over time, and quickly have a sense of their change in rank compared to the previous year. The most important thing of this framework is also that users can go there and can change on any of the parameters, any of the weights, any of the tunable parameters that I've mentioned so far, which means they can customize the rankings based on specific features of their environment. Still have a few minutes, 7-8 minutes. So the last piece that I want to go over, which builds upon these metrics and the model that I've described earlier that connects attack and dependency graph, is this generalization of the traditional notion of attack surface. So traditionally, an attack surface of a system is being defined as the set of entry points that an attacker can use to essentially penetrate the system. And this is based on NIST definition of attack surface. Now, the problem with this definition is that they are superficial in the sense that they look at the surface of the system, they look at the entry points, they don't have a way to measure the true effects or the true exposure resulting from those entry points. So in other words, we need to try and consider the cascading effects of an attacker exploiting those entry points at the surface of a system. Now, to explain that concept, we like to use this analogy. So suppose you have a thief that wants to steal this gold from this room, okay? Now, without any additional knowledge of the internal structure of this house, you would think that the easiest way for the attacker to penetrate your house and steal the gold is to go through the front door. Through the garage door that has a higher exploitability. But if you have more information about the internal structure of the house and you realize that between the garage and the house there is an additional door with the lock, then you realize that the path to penetrate the house from the garage is actually harder than the path to penetrate the room with the gold from the front door. And that's the inspiring principle behind this notion of attack volume that I'm going to describe. We need to look at not just the surface, but what is beyond the surface, and really have an understanding of the internal structure of the network to fully assess the consequences of any of these exposures. So to translate this gold thief example in a more cyber-like example, if you have these two different networks, Each one has a database with an asset value of 100. Each one has the same vulnerability V1 with an impact score of 50%. So at the surface, these two systems are equivalent. You would think they're equivalent, and they deserve the same level of protection. But then if you look at the internal structure, you will see that the one on the left, the database on the left has several different applications that rely on it. The one on the right only has one application that relies on it. So now it's clear that exploiting V1 in network A could lead to much more severe damage than exploiting the same vulnerability in the other network. And this is what we need to be able to capture. So that's how we need to try and assess the true impact of exploit of vulnerability that exists at the surface of a system. Now, to do so, what we did was to come up with a way to try and formalize existing attack surface metrics into families of metrics or generations of metrics. And the criteria that we use to decide which generation each metric belongs to is based on what kind of information that metric takes into account. So we came up with 5 generations of metric, and generation 5 is what we call attack volume metrics. So to give you an idea of how to reason about this, suppose you have 2 systems, and the only difference between 2 systems, A and B, is the fact that one of them has one more vulnerability on the attack surface. So if you have no other information about those 2 systems, the only thing that you can conclude is that probably the one on the right is overall the vulnerabilities in the system on the right are more severe because it's 3 vulnerabilities versus 2. There is no other information that can help you discriminate or assess these 2 different networks. So in this case, a simple attack surface metric that counts how many vulnerabilities are on the attack surface would be sufficient to discriminate between these 2 systems. But now suppose that in addition to knowing which vulnerability exists, you also have an assessment of their likelihood of being exploited. Now, if you have that information intuitively, you can say, the one on the right now is more exploitable because the exploitability score is higher. But if I'm using the previous metric, which simply counts the number of vulnerabilities, it would be 2 versus 2. There is no way that metric can tell me that the one on the right is more severe. So generation 2 metrics would be metrics that take into account the exploitability scores, so they can be able to discriminate between these 2 different scenarios. And that property is true for every generation. So for every generation, the question to ask is, are metrics from the previous generation are able to discriminate between 2 instances here? If not, then the previous generation metrics are not sufficient. Now, moving forward, let's consider these 2 scenarios where now everything is equal. Number of vulnerabilities is the same. The exploitability score is the same for all of those. Now, based on the previous generation 2, you would not be able to tell the difference between these 2. But now what we know is that in the case on the right, the exposure factor is higher, which means that once those vulnerabilities are exploited, the impact is double of the impact in the case on the left. So now we need something more sophisticated to be able to capture this information. And that's where generation 3 metrics come into play. As you can see, and I'm not going to go into details of the equation, but you can clearly see that the equation for generation 3 metrics takes into account both the exposure factor and the likelihood. Moving one step further, now we have 2 scenarios that are identical, with the exception that the one on the right has one additional vulnerability that can be exploited once the vulnerability on the attack surface has been exploited. In other words, there is an attack path that the attacker can initiate by exploiting a vulnerability on the surface. Metrics from the previous generation won't be able to, capture this difference. So that's why we need a more sophisticated family of metrics here who can capture information about attack paths. So generation 4 metrics are the ones who are able to capture information about dependencies between vulnerabilities and attack paths. And then finally, which leads to generation 5 metrics or attack volume metrics, now we have two scenarios that are identical, except for the fact that in the one on the right, there is an additional component H5, which depends on H4, meaning that if H4 is compromised, not only H4 is damaged, is inflicted some damage, but in this case, that damage propagates to H5. So we want to take that into account to fully assess the true impact of the exposed vulnerabilities. Again, we need a new family. I think I missed one slide. Okay. So we need, I missed the equation for this, but it's okay. So the generation 5 of metric is the one that would take into account also information about dependencies between components and how damage could propagate through those chains of dependencies. So to conclude, this presentation, my research overall is focused on these two complementary areas: cyber situational awareness on one side, adaptive cyber defense on the other, trying to converge toward a solution that would help leveling the playing field for cybersecurity. The work on vulnerability analysis that has been the focus of my focus for the last 2, 3, or more years is to improve cyber situational awareness, because essentially it increases your ability to understand the systems that you're protecting, but it's also a way to adapt to a evolving landscape, because new vulnerabilities are discovered constantly, as I was discussing. In a dynamic environment where you use virtualization, machines can come and go, and with them, vulnerabilities can come and go. But also, this knowledge can inform deceptive strategies, and it can inform solutions to try and mitigate potential attacks. In terms of work in progress or future work, last few months I've been working on solutions to automatically map vulnerabilities to CWEs based on their textual description, which is the first piece of information that is available when a new vulnerability is discovered. So when a new vulnerability is discovered, the first information that you have, it's a description of what it is. And this happens even before that vulnerability goes to MVD and is assigned an official CVE number. Also, one thing that I'm planning to work on is predictive analytics to try and anticipate trends in vulnerability scores. And last but not least, as I mentioned before, one limitation in this area is that there are a lot of different tools which are not integrated. So ideally, we want to move toward a solution where you can offer vulnerability scoring as a service, okay, sort of a cloud delivery model, and everything else under the hood is connected to provide this capability as a service to consumers. And last but not least, all the work that I've been, covering over this set of slides is being funded in part by all these entities: Army Research Office, Office of Naval Research, PARC, Palo Alto Research Center, as a sub-award of DARPA and a National Science Foundation.
Thank you so much, Dr. Max, for your presentation. It was very interesting to hear about, people talk about different attack, but you focus until on scoring side. That was very interesting, taking a new dimension of the speaker series that we have actually seen. So we are going to take some questions, and maybe I'll start with a couple of questions. Now, yes, I understand the scoring process, what you do, but do you actually consider the phases of vulnerability? You score this vulnerability right now. It's still a vulnerability right now at this time, TI. But what is the likelihood that this vulnerability can transition into an attack, or in your scoring analysis? Are you in the, I think I understand the CWEs that you're using directly from some database, but I wonder whether have you considered that propagation of the likelihood portion? I think you have something in your metric. Talk about that.
So let me go back to the
exploitation likelihood. Okay, must have missed. Okay.
So, so each of the X that you see here, so this is a sum over X. So the XL with the up arrow is the set of variables that can increase the value of the likelihood. And what I mean by that, if the value of that variable increases, then the corresponding likelihood increases. One of those, for example, as I was mentioning, being the age of a vulnerability. So today, a vulnerability is a certain likelihood of being exploited. But if you recompute this score a year from now or 6 months from now, that score will change simply because now that vulnerability is older. And if it's older, increases the chances that in the meantime, the hacker community has developed exploit skills, knowledge to exploit that vulnerability. So yes, the likelihood will change if you factor the age as one of the variables in this equation. Yes, the score of that vulnerability, the exploitability score changes over time.
And also
becomes, just by virtue of aging, it becomes more likely to be exploited. The way you can counter the effect of aging is by developing, let's say, intrusion detection rules. So when the vulnerability first comes out, maybe there is not yet an intrusion detection rule. So attackers can take advantage of that window of opportunity when the vulnerability is just been discovered. There is not much knowledge about how to detect exploitations. Therefore, they could potentially exploit it going undetected. But if you detect a vulnerability, that increases one of the variables that are at the denominator. And if the variable at the denominator increases, the likelihood decreases.
Great. Follow-up on questions on the exposure factor. You mentioned this is actually coming from additional factors where, maybe the system may depend on something on degraded components. Do you have a database for this, or you separately compute this exposure factor by means of some understanding about the system?
So the exposure factor is decoupled from the actual asset value because it's a relative score. It says if this vulnerability is exploited, 50% of the asset is compromised. Now, the way this is captured in CVSS is through the impact score, the impact score portion of the severity score. And that in CVSS, it's a number between 1 and 10. And it's broken down, as I was showing in this slide, it's broken down impact on confidentiality, impact on integrity, and impact on availability. And it's a very coarse grain. It's low, medium, high. So the impact score from CVSS is one of the X's in our equation for the exposure factor. And in our, let's say, experiments or evaluations, one other variable that we have considered is the, let me go to that line, is the set of deployed IDS rules. Now, why I'm making a distinction between non-IDS rules and deployed IDS rules? If the attacker knows that there exists a rule for a given CVE, they may not know if the rule is actually deployed in your system or not, but they know that it exists. So there is a potential for that vulnerability exploit to be detected. So that may represent a disincentive for them to exploit that particular CVE. They may just opt for another one. The deployed IDS rule, instead, it's a rule that is actually deployed in your system and can detect a actual exploitation. And if it allows you to detect an exploitation early on, it may help you mitigate the consequences because it can can give you an early warning. Okay, look, this vulnerability is being exploited, so you can take action to remediate that exploit as soon as it happens or before it's even complete. And you could have a custom IDS rule that is not public, that is not in the public IDS rule repository. It's a craft IDS rules that the attacker is not aware that it even exists. That rule can contribute to lower your risk, to lower your impact by offering you an early mitigation opportunity. So it reduces the exposure factor. Yes, you're still exposed to that vulnerability because the vulnerability is not being patched, but you have a mechanism to detect right away that is being exploited and to take some action. So that's why we distinguish between deployed and known.
Great. We have a question.
And again, this was just to give an example of other things that you can, what is the logic of factoring other information into this computation? It's not just what CVSS gives you, but it's any information you can derive about vulnerabilities in your environment that can help you either adjust the likelihood or adjust the exposure factor, whether it's adjusting up or down.
Mm-hmm.
Yeah.
Right. Let's see. We have a question from Dr. Utku Kose, and he's asking if there would be a need for new scoring approaches for CVE and CWE in the future, considering AI factor and its impact in expanding cybersecurity scope. How do you read that question, considering that now that you have large language models are popping up, maybe you talked about automatic mapping, how do we handle this?
If there is would be a need for new scoring. Well, so I mean, there is one piece of work that I mean, we're starting to take some NLP into this. There was one piece of work that I just mentioned, but there was not enough time to cover that as well. Where we, I mean, of course, we can expect that the number of potential vulnerabilities being discovered could increase, simply because, I mean, vulnerabilities exist in software. They always existed. And sometimes it can take times to discover them. So one possibility is that attackers using AI techniques doing software analysis may be able to discover more zero-day vulnerabilities. Okay, so that is one risk. So that is part of also of the work that I'm expecting to do on predictive analytics. What kind of trends can we anticipate? So one thing that we started doing, and we got pretty good result. We just submitted a paper to Cycrypt and it got accepted. So based on the textual description of vulnerabilities, which is the first piece of information that you have. So as soon as a vulnerability is discovered, even if it's a zero-day vulnerability, you have somebody describing what it does, what it is, okay? And it could be even a hacker describing that vulnerability on the dark web, okay? So if you could, put your hands on that textual description of a CVE, we can map that to a CWE by just analyzing the text. And what we did essentially, we represented CWEs as TF-IDF vectors. And when we have a new CVE description, a new vulnerability description, we extract its TF-IDF, compute its TF-IDF vectors, and then compute the cosine similarity with all known CWEs, and we rank possible CWE labels based on their cosine similarity between TF-IDF vectors. Now that helps us at least get a sense of what is trending in terms of new vulnerabilities. Because the other important thing is in this metrics for computing CW scores, one factor is knowing the average severity of CVEs in that CW category. But if there are a lot of CVEs, potential vulnerabilities that have not been added officially to that CW category, we cannot factor them in. If we can anticipate, if we can beat the manual process that NVD and MITRE use to classify and officially assign a CVID and then map them to CWEs, if we can do, as soon as somebody describes the vulnerability, we can factor all that information in this system of metrics.
Cool. Thank you.
Certainly. I mean, and this would be one topic for our proposed center.
Yeah.
The role of AI in all of this.
Yes, I think, I have one final question and then we can conclude. I think, I really love the aspect of when you talked about, how that CW79 got down to at the end in the ranking when we talk about system specific, and there is only a subset of that CWC is present in that system specific environment. And also looking at your very first slide, going from perception, comprehension, projection, and looks like so are we saying that we probably need to design the scoring mechanism, that are, how do we go to more customizable, which we do not know, but knowing that what CW is there in this particular system, right? You have for this example that you have talked about, makes sense because you roll the computation scoring every month. It's not a real-time scoring. But I'm looking at, where you have a complex real-time time series systems where you need to catch these anomalies and as quick as possible, and which we could model as vulnerabilities. But I don't know. I'm just trying to pull up a brain on how do you comprehend that second block that you had that needs some further exploration so that we can able to dig in to see maybe a combination of LLMs may be needed for system-specific automation to figure out, to re-rank, whatever what you see. I'm just curious to see what's your thought on that.
So you're talking about
what processes could go in actually going from a broader scale of what you have a generic system, but you want to go into a system-specific CWEs, but I don't know, how do you handle that? It's easy to show from a database, what you can able to handle, but I wonder when the system is so changing, CWEs are changing, and I don't know, maybe it's just a mouthful of loaded question.
Yeah, I mean, CWE are changing, but not as, our CWEs are not changing as frequently as, CVEs being added to MVD. I can share the paper and the conclusion that we got from this paper. One of the conclusions being that CWE itself, the system that MITRE uses to organize CWEs, those CWEs, if you think about it, they're organized hierarchically. And there are certain CWEs that are subset of other CWEs. And the way we sort of found out indirectly from the data that we analyzed is that we ended up doing a lot of misclassification errors when trying to map CVEs to CWEs. And there were very frequently occurring, types of errors, and those corresponded to CWEs that were very similar. So one of the outcomes of that piece of work is, number one, is there a better way to describe vulnerabilities so that they're easy to analyze using NLP and LLMs and so on and so forth? Because one of the issues is those different vulnerability descriptions are written by different individuals and with different writing styles, different level of technical expertise, different use of language, and so on and so forth. So there may not be consistent from a language point of view, and that's where LLMs may have, troubles. I mean, LLMs are very good at distinguish between different writing styles, okay? And in fact, one experiment that we did in a completely different field on misinformation detection, we had because I'm doing some work in election misinformation, so we had real tweets about elections extracted from Twitter and a bunch of tweets generated by LLMs. Okay, we mixed them together and we asked humans to tell us which ones were human generated and which ones were LLM generated. They couldn't tell. We did it through a clustering algorithm, perfect results. So machines can distinguish between, human generated and LLM generated because it's what is called an authorship attribution problem. So you're trying to attribute authorship to certain pieces of text based on the style, based on the specific language and style used within those texts, okay? And that's something the machines are very good at. But as a human, I present you a tweet, and then I present another one, and then you don't keep track of all of them, and then start to think, oh, maybe tweet number 1 and number 5 and number 7, they look written by the same person, right? And maybe that person was an LLM. So, going back to the CVE description problem, one input could be, how can the outcome of this work can be leveraged to understand how can we improve the description of CVE, CWEs in a way that is more accurate, more systematic? How can we improve the CWE hierarchy itself? I mean, is the one that MITRE has the ones that makes the most sense, or it needs to be revised to better capture the different types of CVEs? But as I was pointing out, the reason why we have the work that are shown in this slide is because the idea of those genetic CW rankings by MITRE, I mean, it's a reference work, but it's not useful in practice, because as this example shows, I don't care that CWE 79 is the top most severe ones. If I don't have any vulnerabilities that fall in that category, why should I care?
Very, very well said. I think makes sense. Thank you so much, Dr. Max. I think we're running out of time, so we're going to close the webinar. And as part of your contribution, you'll receive a nice plaque from UND and also a nice certification from our dean. Thank you so much for your time.
Thank you so much for the...
And we look forward to working with you. I think you have a unique expertise that that I haven't heard many, but I think this is actually going to help in some of the proposals and projects that we may go after. Thank you.
Thank you. Thank you all. Thank you for your time.